In this video, we're going to talk about how to solve problems associated with rotational kinematics. So let me give you a list of formulas that you need to know. So on the left side, we're going to put all of the linear equations that is associated with translational motion. And on the right side, all of the angular equations that's associated with rotational motion. So the first equation that you need to know is if an object is moving with constant speed. That is, if it has zero acceleration. So d is equal to vt. D can be used as displacement or distance. Distance and displacement is the same if an object moves in a straight line without changing direction. Angular displacement is equal to omega times t. Notice the similarities between these two equations. So v represents linear speed or linear velocity. Omega is angular speed or angular velocity. D can represent displacement or distance depending on how it's used. Theta can be angular distance or angular displacement. Now what about if an object is moving with a constant acceleration value? So then we have these equations. V final is equal to V initial plus AT, where V final could represent the final speed or final velocity. In the angular universe, it's going to be omega final is equal to omega initial plus alpha t. So whenever you see an A, replace it with an alpha. Now the next equation that you need to know is this one. V final squared is equal to V initial squared plus 2AD. And the angular version of that equation is omega final squared is equal to omega initial squared plus 2 alpha times theta. So anytime you see a D, replace it with theta. If you see a V, replace it with omega. And if you see an A, replace it with alpha. Now the third equation that you need to know is this one. D is equal to V initial t plus 1/2 AT squared. And on the other side, it's going to be not omega, but theta is equal to omega initial times t plus 1/2 alpha t squared. And there's one more equation. The displacement is equal to the average speed or average velocity, which is the sum of the initial and the final velocity divided by 2 times t. So this is a variant of this equation. Instead of using v, you're using average v. So omega is theta is 1/2 omega initial plus omega final times t. So you may want to write down these equations for the problems that are about to come shortly. Now there are some other equations that we need to add to the list. The first one is this one. Linear displacement is equal to the angular displacement times the radius. Now perhaps you've seen this equation in trig as arc length is equal to the angle in radians times the radius. It's very similar. Now the next one, linear velocity, is equal to angular velocity times the radius. And linear acceleration is equal to the angular acceleration times the radius. Notice how similar these three equations are. So make sure to add these three equations to your list. Now let's start with this problem. A wheel spins at a constant angular speed of 24 radians per second. How many revolutions will the disk go through in 5 minutes? So we don't have any acceleration in this problem. So the main equation that we need is theta. I'm not sure what happened there, but theta is equal to omega times t. Now we have omega, which is 24 radians per second. And we have the time in minutes, but we need to convert it to seconds. 1 minute is equal to 60 seconds. So 5 minutes is going to be 5 times 60, which is 300 seconds, which I'm going to put right here. So if we multiply omega in radians per second by the time in seconds, this will give us the angular distance in radians. So it's 24 times 300, which is 7,200 radians. Now we need to convert this angle to revolutions. So what you need to know is that 1 revolution is equal to 2 pi radians. 2 pi radians is 360 degrees, and that represents a full circle. So take 7,200 and divide it by 2 pi, or 6.28, and you should get 1,146 revolutions. So the wheel is going to make 1146 complete cycles, or complete revolutions, during the 5 minutes. Now let's move on to part B. How far along the ground will the wheel travel at this rate in 5 minutes? So here's the wheel, here's the ground. We want to know what is the linear distance as opposed to the angular distance. So how can we get this answer? So recall that arc length, or linear distance, is equal to theta times r. But we need to use the angle in radians, not revolutions. So it's going to be 7,200 radians multiplied by the radius, which is I didn't give you the radius of the wheel. So that's the one thing I forgot to do in this problem. So let's say the radius of the wheel is 2 meters. So that means that 1 radian will have an arc length of 2 meters. So the distance that the wheel will travel is 7,200 times 2. So that's going to be 14,400 meters. So that's the answer to part B, if the radius of the wheel is 2 meters. Now let's move on to number 2. A disk speeds up from rest at a constant rate of 2.5 radians per second squared. What is the final angular speed of the disk after 18 seconds? Well, let's write down what we know. So we know the initial angular speed is 0 because it starts from rest. Our goal is to calculate the final angular speed. We're given the angular acceleration, it's 2.5 radians per second squared, and we know the time is 18 seconds. So what equation contains these 4 variables? So the equation that we need is this one. Omega final is equal to omega initial plus alpha t. Omega initial is 0, alpha is 2.5 radians per second squared, and the time is 18 seconds. So this will give us the final angular speed in radians per second. So it's 2.5 times 18, which is 45 radians per second. So that's it for part A. Now what about part B? How many revolutions will the disk go through during this time period? So what equation can help us to calculate the angle theta? Theta is equal to omega initial times t plus 1/2 alpha t squared. So omega initial is 0, alpha is 2.5, and t is 18. So theta is 405 radians. Now we need to convert this to revolutions. So 1 revolution, as we know, it's 2 pi radians. So let's take 405 and divide it by 2 pi. So you should get 64.46 revolutions. So that's the angular distance that the disk travels during this time period. Now what about part C? What is the linear speed of a point at the edge of the disk after 18 seconds? Keep in mind the final angular speed we said was 45 radians per second. It was 18 times 2.5, and that's how we got that answer. So to find the final linear speed from the final angular speed, it's just omega times r. So we just got to multiply these two values. And we have the radius of the disk. It's 50 centimeters, which is equivalent to 0.5 meters. So keep in mind, 100 centimeters is equal to 1 meter. So you got to divide 50 by 100 to get 0.5 meters. So the linear speed after 18 seconds is going to be basically the final speed at that time. So it's omega, which is 45 radians per second, multiplied by the radius, which is 0.5 meters per radian. So when the angle is 1 radian, the arc length is 0.5 meters. So 45 times 0.5 is 22.5. So we have a final angular speed, not angular speed, but final linear speed of 22.5 meters per second in this problem. So that's the answer to part C. Number 3. A disk with a diameter of 60 centimeters speeds up from 20 radians per second to 40 radians per second in 5 seconds. How many revolutions will the disk go through during that time period? So how can we find the answer for this problem? Let's make a list of what we know. The initial speed is 20. The final angular speed is 40. T is 5. And we have the radius, which is 1/2 of the diameter. So the radius is 30 centimeters, which is 0.3 meters. So when you're asked to find the revolutions, you need to find theta first, which is going to be in radians, and then convert it to revolutions. So what equation should we use in order to calculate theta? I'm going to use this one. It's the average angular speed multiplied by the time. And the average angular speed is basically the sum of the initial and the final angular speed divided by 2. So it's 1/2 omega initial plus omega final times t. So the initial angular speed is 20, the final angular speed is 40, and the time difference is 5. So if you add 20 plus 40 and divide by 2, this will give you an average angular speed of 30 radians per second. So we're going to multiply that by 5 seconds, and so the unit seconds will cancel. 30 times 5 is 150. So the angular distance is 150 radians. Now let's convert it to revolutions. So let's take 150 radians and convert it to revolutions. So 2 pi radians is equal to 1 revolution. So 150 divided by 2 pi is 23.87 revolutions. So that's the answer to part A. Now let's move on to part B. What is the average angular acceleration of the disk? So what do we need in order to find it? It turns out that we already have everything that we need. So we can use this equation. Omega final is equal to omega initial plus alpha t. So if you solve for alpha, you got to move this to this side and then divide by t. The average angular acceleration is going to be omega final minus omega initial divided by t. So it's the final angular speed of 40 minus the initial angular speed of 20 divided by 5 seconds. So the change in angular speed is 20. So 20 over 5 will give us the average acceleration, which is 4 radians per second squared. So that's the answer to part B. Now part C, what is the average linear acceleration of the disk? The linear acceleration is the angular acceleration times r. So it's going to be 4 radians per second squared times the radius of 0.3 meters. So 4 times 0.3, that's 1.2. So the average linear acceleration is 1.2 meters per second squared. And so that's it for this problem. Now let's work on the last problem of this video. A wheel with a diameter of 80 centimeters speeds up from 30 radians per second to 80 radians per second. The linear acceleration of the edge of the wheel is 15 meters per second squared. How many revolutions will the wheel go through during this period? So all we got to find is theta in this problem. And we know the radius is half of the diameter, so it's 40 centimeters. And if we divide that by 100, that's 0.4 meters. The initial angular speed is 30. The final angular speed is 80. And we're given the linear acceleration, which is 15 meters per second squared. Well, if we have the linear acceleration, we could find the angular acceleration. So the angular acceleration is the linear acceleration divided by r. So that's 15 divided by 0.4. And so the angular acceleration is 37.5 radians per second squared. So now we can calculate theta. So the equation that I'm going to use is this one. Omega final squared is equal to omega initial squared plus 2 alpha theta. So solving for theta, I got to move this to this side where it's going to become negative and then divide both sides by 2 alpha. So theta is going to be omega final squared minus omega initial squared divided by 2 alpha. So the final speed is 80, the initial speed is 30, and alpha is 37.5. So 80 squared is 6,400, 30 squared is 900, and 2 times 37.5 is 75. 6,400 minus 900 is 5,500. If we divide that by 75, this is going to be 73.33 radians. Now, we need to convert it to revolutions. So we need to divide it by 2 pi radians. And that's a terrible looking 2. So this wheel is going to go through an angular distance of 11.67 revolutions. And so this is the answer.